the Glasgow notes, it just gives you like this kind of equation, but didn't really explain much. So what I'm going to do is to write down a little bit of things to explain. You'll find that I'll still be repeating some of these equations out there, but I'll write it out. You can write after me, or you can just fill in whatever gaps that you can find. So in your robotics lab, very often times you get to face this sort of situation where you have your motor, and then connecting to the motor will be this gear reducer. So the gear reducer over here smaller, and the other part there bigger. And later on I'll tell you why it's always arranged in that way. And then you would have the inertia of the shaft before you will experience the load. Right? So this kind of sketching it out separately in that way. Normally you just have a load, but within the load you also experience certain amount of damping, and certain amount of inertia. It's probably difficult for you to imagine, but if I have this as a shaft, and then there's a gear that's connected to it, and then I kind of like rotate this really fast, and that gear would correspondingly start to be actuated. But do you think there's a little bit of twisting in that shaft? Very small little bit. And as the gear teeth would rotate through the air, there's going to be this friction forces that you experience in the air as well. Very little bit. Yeah. So all this is going to contribute to a certain amount of damping that will experience. So that amount of damping, we represent it by that knob. And same as your motor over here, you have some amount of damping because of the shaft deformation. It's actually made to be pretty steep, but if your load is high, and if you put a gear that's not much of a load, if you put like pulley system and then a winch, something that's really heavy, I think there's quite an amount of damping that you experience. So how do you imagine damping? You can imagine damping by thinking, if I were to rotate this very fast, and then the whole thing, the winch is being rotated, and stop it suddenly, do you think this thing is going to do a little bit of oscillation? If you think so, that means there's some amount of damping. If it stops immediately and doesn't move, it doesn't oscillate at all, that means it's no damping. Then something tells us that just that little bit of oscillation when it stops. So whenever there's oscillation in your dynamics and control, going up, down, decay, means there's a certain amount of damping. So let's have a look at this mathematics. I need to give you a little bit of convention. For example, this omega thing that we were talking about, that is angular velocity. In our case, theta dot is also angular velocity, the other side here. I think dynamics control you learn in terms of theta dot and then theta dot dot. So that's your angular velocity, and theta dot dot, that is your angular acceleration. So if I have this if I have a cylinder, it's rotating with a certain amount of torque, certain amount of angular velocity, and it has certain amount of inertia, right? For any cylinder, there's going to be a certain amount of inertia. I can say that T, torque, is equal to I omega dot. And I think dynamics control, you use I theta dot dot. Right? And you say sum up your moments. So in this case, instead of moment is the amount of torque. So I theta dot dot. If it's linear system, then you say F is equal to ma, but rotational system, you say torque equal to I theta dot dot. Okay, so there is that kind of resemblance. So for N, over here, N will be defined as the notes didn't really say that. N is your gear ratio. I know you have seen just now before it's represented by G. And over here it starts to use N for the rest of it. In fact, for the rest of your notes it's all N. So I don't know why you do that in Glasgow, but we stick to N as the gear ratio. And in fact, they are a little bit more specific. They say this is a gear reduction ratio. So maybe gear ratio is G and gear reduction ratio, they use N. So N is actually equal to T load divided by T motor, or TL over TM. So that L over there, all these L's, all the L's represent load, and all the M's over there, they represent motor, right? It stands for motor. So I can write TL is actually equal to NTM, or I can write TM is equal to TL over N. And later on, I'll make use of this relationship. So for a rotating system, the rotational energy, in linear system we call it that energy as force. So in rotational energy, that is TL theta dot L must be equal to Tm theta dot N. Torque multiplied by angular velocity. That's your rotational energy. So I can adjust this a little bit by taking TL over Tm and then equate it equal to theta dot M over theta dot L. Just doing a little bit of manipulation for that. This is what we call the gear reduction ratio, N. Right. So gear reduction, not necessarily that you can only find it through the radius or angular velocity, but you can also find it out by you have means to measure the torque or means to measure the amount of angular velocity. That's something that you saw just now. So that can also be possible. So that means N can be represented by theta M over theta L, and I'm going to re-express this theta dot L over theta dot M over N. And hence, if I were to differentiate this another time, theta dot dot L, it must be theta dot dot M over N. So that's how all these equations came about in a set of notes. Just kind of like giving you a little bit more details for that. Now once we have that, let's focus on this figure over here, just the motor and the reduction gear, that part. Again, Glasgow will just give you that set of equations, so I'm going to walk you through how to get these two sets of equations, both for the motor side and the other one for the load side. And after that mathematics, I'll tell you some insights that we can get through these calculations. So let's see, for this case, for the motor, for a for the motor, summing up the torque must be equal to I theta dot dot. So in our case, by summing up the torque seen by the motor, you have Tm, that's the motor torque, minus TL over N. And why summing up the torque gives us that? This part here is because this is called the net torque acting on the motor is the difference between the input torque and torque applied to the load. That's why we take the torque of the motor minus away the torque that came about because of the the torque that's applied to the load. So that's on the left hand side. On the right hand side, the moment of inertia, Im for the motor, and theta dot dot m. M plus one more. This one would be dm theta dot m. So in your dynamics control, this is where your damping component is going to come in. In real life, this damping is actually quite small unless you have a load that is huge and experiences a lot of viscous drag due to the air friction. Then this term will become big. But you can see a lot of mechanisms, a lot of loads that the motor is carrying. Usually you don't experience a lot of air friction. So usually this term is small. So this one here is your rotational damping. So you just put like in dynamics control, you learn it as Cx here. Cx dot here. So I call this equation 1. And for the load, looking at this figure for the load, if we sum up the torque, that's equal to I theta dot dot. For the load side, that will be TL is equal to I L theta dot dot L plus DL theta dot L. Again, this and that. These are your viscous damping coefficients of friction. For M is for motor, L is for load. Yeah. And I call this my equation 2. So if I were to substitute equation 2 into equation 1, so equation 2, that's TL substituted inside here. So I can have Tm that's equal to, if I were to simplify it and bring that term to the right hand side. So I'll have Im theta dot dot m plus Em theta dot m, that's this part here. And then plus 1 over n I L theta dot dot L plus DL theta dot L. Right. Just substituting it and then bringing it to the right hand side. And I'm interested to change this theta dot dot L and theta dot L. How to change that? Because I know that for theta dot L is equal to theta dot m over n, and for theta dot dot L, that's theta dot dot n over n. So I'm going to replace this and that into Im theta dot dot m dm theta dot m plus 1 over n, and the rest of it, that will be I L theta dot dot m over n plus dl
theta dot m over n. So that will give me the n as a common factor that I'm going to take it out. So that will give me 1 over n squared. And IL theta dot m plus BL theta dot m. Right, just taking that common factor of n. And I'm going to group together theta dot m, and group together theta dot m and theta dot m, grouping it together. So I'll get Im plus IL over n squared theta dot m plus dm plus dl over n squared theta dot m. So that's the final form that was given in your set of notes, right? That one over there. So I'm going to give you some insights now. This term over here, this one is my effective load, inertia. In dynamics control, maybe you wrote I effective that way. The units kilogram meter squared. And this whole thing that's in the circular bracket, that whole thing over there, this is what we call the total inertia, represented by I total.
So what I'm trying to do over here, you will see Tm equal to this entire expression over here. Tm equal to that entire expression, where this part refers to the acceleration, that part refers to the damping. And this thing over here, over there, it's revolutionary. Why is it revolutionary? It's telling us something. If you use a motor, put it to a reduction gear, and use that to carry a load, what happens is that the inertia that you experience in the load will be divided by n squared. This is good news for us. What does that mean? It means that now if I were to use a motor connected to a reduction gear to move a load, on my motor side, I actually, if I were to accelerate, I don't feel much of that load inertia. This is good news because now I can use this design to carry a load that's really massive, a lot of inertia over there. That inertia after that reduction gear n will be reduced by n squared. That's a lot. So if I were to use this motor hence to accelerate something, I don't actually feel that something's inertia that much. Don't feel that much. Don't feel by how much? By n squared. So that term is factored over here. I, inertia of the load, will be divided by n squared. And hence, it's actually possible now to connect a motor to move something really heavy, provided you have a good gear reduction ratio. The higher that ratio, the lesser the inertia that you experience. You still experience a load of the whole motor. You still experience the load, the inertia on that load side, but if you have a reduction here, it reduces that by n squared, divide that by n squared. So this is how, in your design, in your robot design, you would want to use a good gear ratio. You think that you cannot move something that fast enough, accelerate fast enough? Here, if you put a gear reduction ratio gear over there, then you are able to move it pretty quickly. that quick thing and deliver that load very quickly.
So what I said just now, I just write it down in words. The motor feels only a fraction of the actual load on the load side, load inertia. And how much of a fraction? There's 1 over n squared, that kind of fraction. So that means with high n, your robot could accelerate, or as a matter, also decelerate quickly. And hence your robot control system can almost ignore your load inertia. So this actually something very, very powerful that you need to know. Oops. So with that, I think in your set of notes, we want to look at some examples. So usually this kind of gear reduction ratios, you want to put it in an order of about 20 to 100. Yep. So that the load, after dividing, that's n squared, will be reduced to 400 to 10,000 of the actual inertia at the load because of the n squared. So gear reduction ratio about 20 to 100. See if you can come up with that using your Lego. If you want to deliver something that has a high inertia at the load, but yet reduce the amount of inertia. Now the same as if you have your motor that passes through a gear reduction and looking at the load that will reduce the amount of inertia, if you look from the load that way, it's the other story, the other way around. Actually multiplied by n squared. So what I mean is that, okay, I'm going to swing this back here.
So what I mean is this. Why is it that we use this part here, having a smaller radius to a larger radius, gear reduction? Why don't we use it the other way around, where we have our motor over here, and then your load apply over here? If you were to do that, having this larger radius, smaller radius, that's not gear reduction here. That's gear increment. I'm not sure if that's good. We don't actually use it in that way. If you're going to use that in that way, that means you're going to experience the load over here. If this gear reduction is 10 times, you'll feel the inertia n squared times. So that's why we don't design the gear, the driven gear to be on the larger gear side. Driven gear is always on the lower gear side, so that we can reduce the load inertia.
So you can see the amount will be increased tremendously. And to reduce this effect, sometimes, if let's say you really need to, sometimes you need to use a slender rotor. So your motor is actually very slender or very flat, like a pancake kind of a motor. So as to reduce the amount of inertia that you'll feel if you are over at the load side, driving it at the load side. Let's have a look at an example. I'll just write out the given things that's in this example. So you still have that same kind of a motor gear reducer, and there's this arm here that has a mass, M arm, and then at the end of this arm there's a load over here that has a mass as well. There's M end, right, M end over there. So there's some given parameters over there. So what I'm going to do is just write it out. We're given the inertia of your motor, that is 0.015 kilogram meter square. You're given the torque that a motor could produce, 8 newtons meter. The length L of that arm, that is 0.5 meters. The mass of the arm, that is 3 kilogram. And the mass of your end, the end mass over there, that's 2 kilograms. And the question asks you to find what is the I total at a condition where n is equal to 3 or 30. Yeah, asks you to find this. This straight line over here is a mathematical shorthand to say under the condition of something. Find I total under the condition of n equal to 3 or n equal to 30. The question also asks you to find your angular acceleration of the motor under the condition of n is 3 and 30. It's trying to ask you to find this too. So let's try to solve it. You have IL is equal to I arm plus I end. Now this moment of inertia, I realized that that was provided into as your exam data booklet in your dynamics control. You have this list of different shapes moment of inertia for that. Like what is the moment of inertia for a sphere that's connected to an axis. Right? All this table in your dynamics control. So in your robotics, it's actually not provided. So I thought what I could do is to make sure that if questions like this that requires that formula, that it will be provided to you. So I'll try to make sure about that in your exam. Because you can't memorize all your list of moment of inertia table, right? That's not right, yeah? So for moment of inertia for a beam, that's 1/3 m arm L squared plus moment of inertia of that m mass, so that's m n L squared. So I'll be able to fill in all these numbers. 1/3 mass of the arm is 3 kilograms, length that is 0.5 meters in square, plus mass of the end mass, that's 2, and length in. So do a calculation, 0.75 kilograms meter square. So that's for the load inertia, where it's a combination of the arm and the end mass. So I need to find out what is the I total. So the I total would make up of the moment of inertia, the motor plus the load, the moment of inertia divided by n squared, since I have a gear reduction gear over there. So IM, that's the one that's given to us. Just write down. IL, I just calculated 0.75. And my n would be in 2 cases. One case is 3, and later on I'll do it for 30. So do that one, you can see that now your total inertia has been reduced to that much. So the same goes for your theta dot m. It's actually T by your I total. So the torque of the motor, that's 8, and the I total, you just find out that's 0.098. So that will give us 82 radians per second squared. So that's the angular acceleration of the motor. Now, you're also asked to find out under the condition of n that's equal to 30. So using the same equation for n that's equal to 30, so in this part here, it will become 0.015 plus 0.75 divided by 30 squared. So that will give us 0.0158. So the same goes for this part as well. This one will be 8 divided by 0.0158. So my theta dot m is going to be 506 radians per second squared.
Now I just solved this question, but I want to give you that insight. There's this comparison between the small n, the small gear reduction ratio of 3, compared to 10 times of that, 30. So this is for the case of 3, or the case of 30. Very large gear reduction ratio. So I want you to be able to see two things. One is that the I total. You can see that the I total for when n is equal to 30 has been reduced drastically. It's square times it. Why is reducing this I total important to us? That's because hence my angular acceleration, I can accelerate it so much more times faster at the n being. So this one for the case where n equals 3, 2 radians per second, that kind of acceleration. Having a gear reduction of 30, I can get up to 506 radians per second of acceleration with the same amount of load. It's just that the n value I've increased. So that sort of thing, when you apply it to your robotics toy construction, it makes you an adult.
Jadi kau beli the kingdom built fleet.
Now let's have a look at another mechanism. Just about. Okay. Now if you need to copy this, actually a lot of it is the same as what is inside. If you need to copy, you can comment over later. But what I want to talk to you is this thing. Remember, there's this rotational and translational motion that we were talking about for the worm gear. Now, the worm gear, you could see that it cannot be the driving gear because that worm gear over there would be the driving gear. If you really want to use this to drive, then you have to use what we call a pinion rack construction. Pinion rack, yeah. The rack and pinion system, yeah. The rack and pinion system says that you have this part here, the spur gear that's rotating as a driving gear to drive this rack over there. So this one over here is the rack. That one over there is your spur gear, or it is your regular gear. Okay. So you can imagine this rack over here, it has gear teeth over there. It's just like an infinite radius gear. So infinite radius going that way. It has a center somewhere in there. So a very huge radius over there, almost like a straight line now. So you can consider it in that way. There's also another way to move things linearly, because now you could connect an object over here, and this object will be able to move in and out linearly while you drive that rotation a rotational spur gear over there, translating a rotational to a linear moving motion. There's another way is to use this ball screw method. So this example is actually not in Glasgow notes here, so I kind of like found this picture, put it over here. So the ball screw is that it has this kind of like a nut, screw and nut system. So if you hang on, if you drive this screw, can you imagine that if this were to lay flat on the ground, this guy here would move either right or left here. That nut would move right to left here when you screw that screw. So there may be some weight or some mass that's acting downward, like heavy equipment over here. So in order to reduce the amount of stress that's acting on the screw thread, you put ball bearings in between. So that ball bearing is able to distribute the load so that the nut and the screw is not like cutting against each other under massive loading. So this is one way of transporting things around, heavy items around. So there's some calculation behind this for rack and pinion. So I'm just going to give you more details about these few sets of equations over here. So you have this bottom part, this is your rack. This is your rack. And then that rolling part there is called a pinion, or just now I use the word spur gear, depends on what's the size of that. Usually for a small size, it's just a pinion gear. So you can apply torque to that pinion gear. It will rotate with an angular velocity. And as it rotates, it's going to move this rack in or out, with a certain output velocity. So the rack, the pinion would have a certain radius and certain output torque that the rack would experience. So let's consider, let's give some definitions. Tin, that is your input torque, and T out, that is your output torque. So if I were to consider the pinion, just a pinion part, and looking at the net torque, what we do is to take T in, the torque that's the input torque, minus the output torque. That must be equal to I omega dot or theta dot dot. I'm keeping it to omega dot so that it's consistent with the rest of the lecture material. So I could simplify this because just to give you a little bit of sight line over here, because we know V is equal to R omega. So V dot is equal to R omega dot. So I'm going to make use of this omega dot is equal to V dot over R relationship, just to replace this part. So T in minus T out is equal to I over R V dot. And I call this equation 1. So that's for the pinion. Now I want to consider the rack. So for the rack, summing up the forces equal to mv dot squared. It's kind of F is equal to ma. So I'm going to make use of that v dot. So acceleration is v dot. And if you look at this figure over here, there's a radius and there's a force that's going to be applied by the pinion that's rotating. So there's an output torque. So the output torque is actually force multiplied by the radius r. So I'm going to make use of that. T out over r minus CV is equal to mv dot. So that's summing up all the forces, right? Because the force is equal to T out divided by R here. I want to find out what is that force. Is that force in this direction? That force. So this part over here is actually your frictional force, and C is your damping coefficient. Usually given Newton seconds per meter. So I can re-express this into T out. There will be RCV plus MRV dot. Call this equation 2. Yeah, just re-expressing this equation over there. So what I'm going to do next is to substitute equation 2 into 1. So T in minus equation 2 into 1, so that T out will be replaced by RCV plus MRV dot equal to I over R V dot. So simplifying it a little, T in minus RCV equal to, there's a common factor V dot, so I'll take it out. I get MR plus I over R V dot. And taking V as the subject, so I'll have T in minus RCV over everything that's in the circular bracket, and I get to this expression. But it's not quite what the notes has provided. So what the notes has done is to multiply R over R to this, and hence you get R over MR squared plus I multiplied by T in minus R CV. Alright, that's the equation that's given to you in your set of notes. I know in your set of notes, instead of using V dot, they use dt over dt. I thought it's easier if I just use V dot instead of dp dt. And V dot is just acceleration. So that's for pinion and rack. There's no example for that. I think in your tutorial there's a tutorial about this, so I'll be uploading that shortly so that you can attend the tutorial for the actuators portion. Let's have a look at this ratchet and ball. You would have heard ratchet a lot already, but I think you have not heard about ball. So the ratchet part, the fact that it can give you the clicking sound, that's because there's this stopper thing that is clicking on it. Yeah? So that stopper is actually called Paul, P-A-W-L, Paul. Okay, that's the one. So number one, this one is called ratchet. And this one is called. So 3 is just a fixed structure. So you can see pretty easily that this part over here can only rotate in this direction, but not the other way. So this is another mechanism to control that doesn't require electronics. Most of the time, this thing will be connected to a spring, right? So that at all times the core will be pushing onto the ratchet. And there's this 2 more slides about the bearing. This one is a thrust bearing, and I just want to bring these two slides side by side so you can see the difference. Yeah. Now, most of the time you'll be dealing with this kind of ball bearing because this ball bearing is used when you have radial loading.
So for example, if you have this as your shaft, how are you going to hold a shaft that's rotating? You need ball bearings. And I've seen before people using ball bearings and hold it in this way and have this end part of the shaft that's hanging out there. And you have some load. The proper way of designing the ball bearing is to hold it at the end, okay? Not somewhere else in that way. So this ball bearing is able to hold it while this shaft is rotating. So this kind of loading by the shaft is actually called a radial loading. But there's some kind of shaft that you need to hang on that is not horizontal, but maybe vertical, and is rotating. So in that case, and you can see that most of this loading, in fact I'm already feeling it here, is axial loading. So when you have axial loading, this axial meaning the axis of this shaft. This is the axis of the shaft. So whenever you have axial loading, you need this kind of ball bearing. You can still support it. It's just that kind of support allows support to be completely in the axial axis, or if you have a combination in this way, that you have radial loading and axial loading at the same time, so you have that kind of ball bearing support. For this kind of bearing is called journal bearing. And the journal bearing, there will be an inner race that will hold on to this ball bearing, and an outer race that you will put to any kind of support stuff. So if you think about it, which part will be the inner race or the outer race? Which part will be rotating? It's an inner race that's rotating because your shaft is protecting your inner race. So the inner race protects your shaft. The inner race will push against your ball bearings radial.
Now, a lot of times you'll find that the ball bearing will get heated up. If you didn't design it properly, you're gonna experience a lot of wear and tear. For example, you can't use a journal ball bearing for axial loading. It can still support somehow, but you're gonna have a lot of heat produced and a lot of wear that's gonna come in. So you need to choose the right type of ball bearing. Okay, that's all I have. Next week I'll talk a little bit about hydraulics and pneumatics.